Hello, my name is Philip Jones, and this is my talk on how we sped up Flask and Quart routing. I originally gave this talk yesterday on the 29th of November at London Python, and the slides are available at pgjones.dev/talks. Okay, before we get into what routing is, let's first introduce Flask and Quart. So if you're going to be familiar with either, you're probably familiar with Flask, but if you're not, they're both web micro frameworks, which means they have all the tooling you need to handle requests and responses in the HTTP sense. For Flask, this is a very typical quick start, and what it says is that a GET request to the root path, i.e. just the /, will be handled by the hello function, with the response being the return value. So in this case, the response is hello world. Quart looks very similar, just with an async, and that's because Quart is the Flask API re-implemented using async await. So these are very similar frameworks that have the same basis, which means they have the same router. But what is a router? Well, routers are what finds the right handler for the request. So that means that the router is what maps the request to a certain function or the handler. So here we have the Flask API defining it, and what we said here that a GET request to /foo should be handled by the foo function. Here we say a GET request to /bar should be handled by the bar function. So the router's job is to take a request, for example, get/foo, and call the foo function. And just to reiterate that, if the request was get/bar, it should call the bar function. In addition though, if a request comes in that's get/other, i.e. something that's not been defined, the router should return a 404 response, so that's the status code, i.e. a not found. And interestingly, if a request comes into a path that matches, but the method does not, the router should return a 405 response, i.e. method not allowed. So this is the basic functionality of a router and what a router does. But it does more than that. And the first thing it does is extract path parameters. And this is a very important feature because it makes it so much easier to write your handlers. So what this means is, and I'll start with a simple example again, a get/API should call the API index function. A get API/ and then this specific syntax means that this part here is a path parameter. So instead of it needing to exactly match less than, val, greater than, it will match anything that fits in with this converter. And then it will pass that value in as an argument to the function. And I've defined this one as well to show that the router should also be aware of when there can be, if you will, conflicts. Here, the value, you could argue, is static, it's attr. So any request that comes in with exactly attr should call this function, not this function with the value equal to attr, because this is more specific. Hopefully that's clear, but if it's not, we'll run through it. So again, get/API should call API index. Get/API/to should call API ID with a value 2 that's a string. It should just pick out the value, which is this part. Get/API/stir, same idea, API ID, but this time the value is stir. But crucially, get/API/attr should call API attr instead. So that's what path parameters are, but they also get a little bit more complicated, and that's to note that path parameters can be converted. So the parameter we spoke about here is what we call in Flask and Quart a string path parameter. And that means it will match anything that doesn't include a /. So it's equivalent to writing this. So here we have it again. This means get API/string value, we'll call ID string with that value. This one gets a bit interesting now because now we're saying it's an int path parameter, an int converter, sorry. This means that only requests that have something that can be converted to an int should call this function with the value converted into an integer. And finally, to point out that these type of path parameters will match anything other than /, we have this one here. So it's API, then a value, then /, then attr. So if that matches, it should call ID attr. So I'll go through the examples, which I hope will make this clear. So a request that is get/API/to, well, 2 can be converted into an integer, so it should call ID int with a value of 2. Next request, get API slash stir, well, that can't be converted into an integer. So we should call id stir with a value that is the string as a string. So str as a string. Next, a request that's get slash API slash 2.2, where you can make an argument here that this could be converted to an integer. In Flask and Quart, however, it doesn't count. There's also a float converter if you want to account for these. So instead, it calls id stir with a string value 2.2. And finally, a get request to slash API slash 2 slash attr calls id attr with a value of 2, not id stir with a value of 2 slash attr, because these converters, especially the string converter, will convert any string value excluding forward slashes. So I just want to emphasize that part there. Okay, so those are what converters are, and Flask and Quart allow for any type of converter you like. You can add your own custom converters, and they're defined using regex, which we'll come to later. So yeah, there's a lot of scope to make this quite useful for your needs. Okay, on the last slide, I made a strong point about saying how the string path converter does not include forward slashes. So if you want to include forward slashes, use a wildcard parameter, in which in Flask and Quart is called a path converter. So this says any get request to effectively anything should call this function. But again, there's a bit of complexity here, which we should be aware of, and that says if we define this route that says any get request to anything that trails with slash edit should call this function, not that one. So to make that very clear, get slash quart, we should call page with the value quart. Get slash quart slash edit should now call edit, again with the value quart, because that's the parameter part. And hopefully, if you follow this, it's all very clear. Get slash quart slash router calls page, quart router, and get quart slash router slash edit should call edit with the value quart slash router. So that's wildcard parameters. And it turns out not all routers will allow you to put anything after the wildcard, like Flask and Quart do. They actually restrict it to only this form. So this is something that I think makes Flask and Quart more useful, but it definitely makes the router much harder to write and is quite a bit of complexity. And I'll show that later on. So what I've said so far is pretty much the standard functionality of any router, with the exception perhaps of this. I'm going to talk about a couple of extra features that Flask and Quart's router provides, but actually make not too much difference to how it's implemented. So I'm going to mention it here, but in the rest of the talk, we don't need to worry about this. What I'm going to talk about is merging slashes and handling trailing slashes. So if we define a route, well, I'm going to be more specific here and call this a rule. So this bit here is called the rule. So if you define a rule that's / branch / leaf with a trailing slash, and a request comes in that's get / branch / leaf /, then if merge slashes is active, this will call index, because it will merge these slashes together into one. If it isn't active, it will return a 404. So that is an optional feature you can use, and is, I believe, on by default. Next, and this one should be obvious, but if we do a get request to / branch / leaf / with the trailing slash there, again it's going to call index. But if we do a request to get / branch / leaf with a missing trailing slash, then the router is expected to return a 308, a redirect request to branch / leaf / with the trailing slash there. So this is an optional feature. It's called strict slashes, but again, it's a way of handling trailing slashes that Flask and Quart provide. But just to reiterate, these are optional features, certainly not present in all routers, but can be very useful. Okay, so now I've defined what router's functionality is. I can quickly mention what Flask and Quart's router is if you want to go and look at it directly, and it's Virksug's router. So Flask and Quart are both built upon Virksug. So it's that library's router that we're going to be talking about today. Okay, so I'm going to start by explaining how it used to work, and I'll go through some examples, and then I'll show you how it works now and try and argue why it's quicker, and show you a bit of benchmarking. So Virksug's router, pre-version 2.2, so pre this summer, this year, used what I'm going to call a regex table. And the way it works is in two parts. The first two actions happen before any requests arrive, so it's kind of pre-computing. Then the last 3 take place for every request. So what you do is you take all the rules that have been defined and you convert them to regex. So a rule such as /API with an interpath converter becomes /API / and then the regex \d plus as a group. So that means this part will match anything that's 1 or more digits. Then, now you've converted all these rules to regex, you order them by weighting. So the static rules come first, and it's based on the complexity of the parameters. Then, now you've built the regex table, we can match requests. So when a request comes in, we try and match the path against each rule in order. So we go down the table. If a match is found, we run the converters on the regex groups, such as this one, and when you run an int converter. And then we return the match and the converted values, which allows us to call the function. So I hope that makes sense, but if it doesn't, here's a few worked examples. So if we take all the rules and functions we've defined so far in this presentation, we get this table. And this is the regex table you build from it. So you can see here, these are the rules, this is what it looks like in regex, and I've ordered this. So all the static parts come first, more specific path converters come before the more generic ones, and rules with more static in come before the rules without. And this ordering is important to make sure it matches the way we expect. And this will become clear as I show you some examples. So, first example, let's match /API. So how do we match that? Well, we check each rule in order. So, does foo match? No. Does bar match? No. Does API match? Yes. So we can call API index. That one's fairly easy. Next, let's do API /to. Foo doesn't match, bar doesn't match, API doesn't match, API /atta doesn't match, but API and then the regex d plus does match, and it will pick out the 2. Now, you can hopefully see why it's important the ordering here, because if this rule here was before this one, this would match first, and we'd never call the more specific int converter as we'd want to. Okay, so that's that. Next, we carry on with API /foo. Foo doesn't match, bar doesn't match, API doesn't match, and we keep going down till we find this match here. And again, this group is going to extract foo, and that's going to be the val passed to this function. And finally, quart /edit. We go down, there's no match, and then we try this wildcard one, and it does match. And once again, you can see why the ordering is quite important, because this would also match, but we want this to match in preference if it can. And once again, it will pick out everything but the /edit as the group and pass that in as the argument. So that's it basically to our regex table router, and its complexity, I would argue, is order mn. So in the worst case, you need to check every rule in the table, and there are n of them. Let's say there's n of them. And in the worst pathological case, you're going to have to check for each rule the entire length of the request path. So it's fairly pathological to imagine that happening, but I think this is fair as saying it's the worst case. So that's a regex table router, and they really are popular. I think they're the most intuitive router to build, and I suspect most frameworks start off with it. And certainly in the Python space, 2 of the big frameworks I know about, Django and FastAPI, or Starlet really, because FastAPI uses Starlet's router, they use regex table routers. So very popular, very stable, and very useful, I think it's fair to say. But you can do better, and you can have higher performance routers, because there are faster algorithms and faster implementations. And Falcon, I think, is the pioneer in the Python space of this. So Falcon have really optimized their router, and this is Falcon's logo, if you're not clear. Sonic then followed Falcon and pretty much implemented the same algorithm and almost the same implementation, or at least the same concept of implementation for their router. So this is also very quick. And then outside of Python, in Go, there's a library called FastHTTP, which I mentioned because it, Sonic and Falcon, all use a regex tree or a prefix tree for their routing algorithm. And the kind of obvious thing to say is, well, why don't we use that for Flask and Quart? Well, it turns out to use a regex tree, you've got to accept some functionality isn't possible. Most notable, you can't have rules like this one. If you have a wildcard, it must be the trailing part of the rule. You can't have stuff after it. So that rules out a regex tree, basically. So that rules out what these use. But we can use something very similar. And I'm going to call this a state machine based on a talk I saw after I've made the change, actually. But I've linked it in this presentation if you want to have a look. So how's this state machine router work? Well, you take a rule and you split it into parts. So this rule here becomes a blank part before the first forward slash, then API, then ATA. So you split it into parts based on forward slashes. Then you build a state machine based on these parts, with each part being a transition between states. And then you order the possible transitions by the same weighting as before, i.e. static rules come first, and then based on the specificness of the parameter, the converter. So you do this beforehand to build the state machine. Then when a request comes in, you then split that request path into parts, again by forward slash, and you transition through the state machine using those parts. If a match is found, you run the converters on the regex groups and return the match and the converted values as you would for a regex table. So I hope that's clear, but if it's not, hopefully this diagrammatic example and the few worked examples I'm going to show you will make it clear. So this is the state machine built up for all the routes we've talked about so far, all the rules. So this is the same as the regex table I showed you earlier. But again, it's quite a simple one, so it's hard to see from this just how or why it would be quicker, but I'll go through that in a minute. So you can see here, these are the transitions, these lines, and they're in order, so you check from top to bottom, and these are the states. So when you reach this state, if there's nothing else in your request path, there's no more parts to match, then you're going to call foo. So let me show you this. So we start with /API. So we start from the root. First part is API, so we transition to this state. Next part is empty, so we transition to this state, and we call API index, as we did before. So that's all good. And just to be clear, when we're matching the first part, we check against foo, no match, check against bar, no match, check against API, a match, so that's how we know which transition to follow. API 2 is very similar. You can see the first part is API, so we do that transition. Now we look at the 2. It's not empty, it's not ATA, but it does match here, so now we know to call ID int, and this match will pull out what needs to be converted and passed in as the value, as the val. Okay, next we do API/foo. So the first part is API, which does this transition. Next part is foo, so again we check down. This is the first time it matches, so we do this transition. Then the final part is empty, so we go here and we call API ID with the val equal to what's been extracted here. And finally, and this is where we actually fall back to the regex table, is when we've got the wildcard. So we've always had this in the definition, I just haven't mentioned it yet. But what happens when you have a wildcard is that you fall back to a regex table, but it only has the wildcard parts in. So whilst these transitions you match against parts of the path, once you get to this table, you do it exactly as you would for a regex table router. So let me explain. So first you split it up. So the first part you're looking at is quart. Does that match foo? No. Does it match bar? No. Does it match API? No. So now you fall into the table and you look at this. Now you match the whole path. So does quart/edit match this? Yes. And we pick out quart as this part. And we call edit with the path equal to quart. So that's a state machine router. And it's quite hard to see on this because I had to make it simple enough to fit on a slide. But what you can imagine now is that say I had a big tree after this node with, I don't know, 10 more roots coming up here, 10 more rules. Then as soon as I rule it out that foo doesn't match, I no longer have to worry about the rest of this tree. So I'm saving a lot of lookouts compared to the table where I'd have to run through them all, potentially depending on the weighting, but most likely I would. So you see, that's how it can be quicker. So let's try and quantify that. Well, the first thing to state is that in the worst case, I think this router has the same complexity. And the reason I say that is in the worst case is everything's a wildcard. Every rule has a wildcard in, so it's just a regex table router. So I think its worst case is the same. But I think it has better performance on average. And if you understood my explanation a second ago, that's because in most rules in realistic routers have shared prefixes. And as soon as you've ruled out the prefix, you don't have to worry about all those rules anymore. So you do less comparisons in the state machine router. But equally, I think it's fair to say that at least algorithmically, this new algorithm, the state machine, will perform no worse than the regex table. It might perform worse due to implementation changes, but algorithmically it should be the same. So I think it's fair to say that on average this will be quicker. So I did benchmark it, and this is how I benchmarked it. What I did was I went to a couple of repos that do benchmarking of routers, and thankfully one of them had a list of 200 rules that were at the time being used by GitHub. So this is pretty good, realistic example, and a lot of rules. And the reason you need a lot of rules is, in reality, as a rule of thumb, you need about 50 or more rules to see this effect take hold, which is, to be honest, what most realistic apps have, most realistic production apps. It's only benchmarking ones that don't. So I have around 200 rules, and so what I do to benchmark it is I create a path that matches that rule, has the right structure, and then I match it in both the new state machine router and the old regex router, so both Werkzeug implementations. And then I measure the ratio of new to old and take a look. So the top 3 rules from this set are all about 5 times quicker, which is very nice. However, the bottom 3 rules are slower, and particularly this one is about 1.7 times slower. So that's kind of interesting, and I think that's an implementation detail to look at. So again, if you want to do this yourself, you can see the script here, and you can see the commit I tested against. But, and this is the kind of bottom line, the new router is about twice the speed on average to the old router. So I don't think it's particularly worse, but on average it's certainly better. So I think it's fair to say that Werkzeug router is now quicker, which means that Flask and Quart are now quicker. Now, again, you probably won't see this in any of the micro benchmarks that everyone loves to share, but you will see it in your real app, in a real production app. Cool. Well, that's my talk. If you want to know a bit more about me, you can find me at pgjones.dev or pgjones on GitHub and pgjones on Mastodon or Fostodon. But on Twitter, there's an extra D, so please look out for that. I'm a maintainer of the Palettes projects, which includes Flask and Quart. I'm actually the author of Quart and a ASCII server called Hypercorn, and I'm a maintainer of the Hyper projects. And finally, if you like the way I explain things, I've written a book. So this book in this book, if you follow it, you'll build a web application for to-dos with a front end in React and TypeScript, a back end in Quart Python, and then it's deployed to AWS in a Docker container using Terraform. So really, it's a book where I hope you learn how to build a web app for all the pieces of web app from scratch. So that's the idea. And I've tried to include as many industry best practices as I can. It's really aimed at like engineers who are just starting in web development, full stack web development, to kind of get a good overview of it all. And if you're watching this talk shortly after I've given it, this discount code or this link here will give you a discount on the book. So thank you. I hope you enjoyed my talk.